IBM Research Distinguished Speaker Service. And today we have Yunyao Li, who is one of our own. So she will be talking to us on an interesting project, SystemT, and she'll be focusing on an algebraic approach to declarative information extraction. Yunyao, as you all know, is a research staff member here and the manager here. She manages this scalable natural language processing group. And her expertise runs from databases to natural language processing to human-computer interaction and information retrieval. She's been with IBM, and before that, she had her PhD in computer science and engineering from the University of Michigan. Before that, she had a dual degree in master's in computer science and engineering and information and computer science from the University of Michigan too. And before that, she had her undergraduate studies in Beijing, China. So today, welcome you to discuss the SystemT.
Thank you very much for the introduction. So it's my pleasure to be here to talk about our work on SystemT. So it's a teamwork. At the end of the slides, I will show you the long list of members that contribute to this particular SystemT. This is the outline for today's talk. I will begin with some concrete case study to show you how we can use information extraction to build newer generation of enterprise application. And then I will talk about what that implicates, what kind of new requirement brings into information extraction. And I will also talk about the challenge for a traditional information extraction system and how we overcome those challenges in SystemT. And finally, I will summarize the talk and give you some discussions for future work. Feel free to interrupt me if you have any questions. Okay. So the first common case that maybe most of you have heard about is using information extraction for sentiment analysis. So now we have all kinds of user-generated content from tweets, from email, and so on. It's basically a gold mine for today's company to identify information that they could never done before. So they want to ask questions like, who can we cross or upsell? What our customers think about our brand? And also, what do our customers want? Instead of brainstorming in a locked room, they can actually go to social media, identify the customer's voice, and help answer all these questions, make insightful decision based on what they learn. So the general process works like this forward. Of course, we have data from social media. In addition, we often have information from internal resources, like what are the products, what we already know about our customer. And by combining those information together using text analytics, we will be able to build 30, 60-degree profiles for each and every one of our customers. We will understand what type of life event that recently happened to them, what is the relationship, and so on. With all this information, we can generate interesting reports about our customer that help us to make better decisions. For instance, if this person just recently graduated, maybe it's a good chance to advise to that person certain products. In order to do this implies multiple challenges. The first is scale. There's so many Twitter data generated on a daily basis, and there's so many consumers there. How can we build a scalable system that can handle such large amount of data? And there's so many different things people are talking about on social media. How can we capture all of those in a scalable way and at the same time be very precise? Then it comes complexity. In order to understand all people are saying on the social media, it's not a simple problem. Sometimes it can be a challenge for us also. For example, giving a Twitter message, you may not even be able to understand it without being playing with Twitter for a long time. Another study comes with machine data. So today's website is no longer one server system. Instead multi-layer architecture. Every single component keeps on generate all kinds of log. Let's say one event happens and you see an error message come out for one of the machines. Now you want to diagnose what's the root cause for that error message. In order to do that, we need to build a system that is able to understand all these logs, pass the logs together, link information from different machines together, and identify end-to-end application sessions, and then generate all kinds of models that can explain what's the relationship between different events, and finally be able to identify the cause. The challenge here is every customer has a unique configuration. So even if you come with one solution for machine log analysis, when you deploy it at customer side, you need to do some customization, and you need to do it really very quickly. And finally, so we have some interesting challenge in one of the recent projects. So we have public data from different resources. We have data from financial reports, newsfeed, websites. And we want to aggregate all the information together through text analytics as well as statistical analysis to answer the question of what's the true production cost for water. And this allows us to build a water cost index that help the different paths involved in water project to estimate the risk and also come up with new financial products. The challenges are a lot of the public data are unstructured, and also a lot of the data are not complete. To give you an example, I may have quarterly reports for the project for first 3 quarters, and then I do not have report for quarter 4, but I have yearly report. So how can I use this information to identify the cost for the 4th quarter? So there are lots of the noise or inconsistency in the data that we need to handle, besides just extracting the useful information out of it. So with all this case study, I hope I have convinced you that text analytics for enterprise application is a very useful but at the same time very challenging problem. And when we talk about text analytics, often it's a very broad definition. So it comes from core operations such as color speed tagging, deep parsing, or detecting individual syntax to actually extract a concept relationship and finally do clustering, classification, all kinds of statistical analysis on top of it. So in this talk, I will focus on information extraction because it's a key enabling technology for text analytics. The input for information extraction is the original text as well as features from lower level large language parsing operations such as color speed tagging or tokens and so on. And the output are structured data that's suitable for feeding into high level applications. And information extraction happens almost everywhere. I show you 3 case studies, but there are many, many places we are using. In order to create a consumer profile, we can go to social media. In order to solve the security and privacy problem, we can go to email, and for machine data, we can look at log. And for financial analysis, we can look at all kinds of financial reports. And of course, the data is like medical records, patient data, news, and so on. So many of you actually deal with one type of data or two in the broader data domain that I'm describing here. And information extraction can be very complex. Besides just giving a plain text, it can come with the semi-structured form like table. So here, for example, from one single financial report that is 136 pages long, I identify some tables, and you can see they look very, very different from each other. And I want to be able to identify certain information from this table. Let's say I want to identify line item for operating expense from this data. As you can see, I will need to identify both the row as well as column and to be able to associate them with each other. So you don't need to go into too much details into exactly how we do this. This example is just to illustrate the complexity of the information extraction task. So just describing this one single case study, maybe we require 1 hour. So don't get too much into this. So another information, we talk about sentiment analysis, but sentiment analysis can be different from domain to domain, from application to application. For example, for customer review, if I'm a competitor of the marine niche, then I heard my competitor's webpage is better. That's actually a negative sentiment for my website, right? And in other domains similar, for example, on social media, I need to deal with, first of all, there are lots of noise in the data. I need to be able to somehow understand this very noisy data and identify different kind of sentiment in it. And you will notice within even one very short tweet, you will see some negative sentiment and some positive sentiment happens in the same Twitter message. When we go to another domain, the sentiment is less explicit. For example, if I say, look at the last one, sell euro and say at market for decline for a certain amount, this is actually implicate some sentiment against the currency pair. So for this particular, for research reports, basically you need a lot of domain knowledge to even understand whether it contains any sentiment message and what kind of sentiment it has. For instance, if you say, we continue to rate share of Microsoft neutral, for a non-domain expert, you would think it's a neutral sentiment. But from the domain point of view, it's actually considered as negative. So I hope I have convinced you that information extraction for enterprise application is a very difficult problem. And the requirement for the first is accuracy. This is a traditional requirement. For any information extraction engine to work well, it needs to produce good results. Otherwise, any application built on top of it will not be able to provide any meaningful information. The second is information extraction, as I have shown earlier, it happens in a larger pipeline. So it's important to have the engine to be able to embed in different systems, in different environments. And the third one is scalability. We need to deal with large amount of data. Instead of a traditional natural language engine that only deal with hundreds or at most thousands documents at a time, we are dealing with data that are terabytes or petabytes in some cases. So we need to have a very scalable engine that is able to process all this data really, really fast. And the fourth requirement is transparency. Even though we can develop different solutions for different kind of problems, for example, we can develop a generic sentiment analysis package, we can develop a solution for machine data acceleration, we need to adopt those solutions for every and each of the customers. And we need to be able to do that efficiently. So we need a transparent system that allows us to do that. And finally, usability. Building information extraction program is very expensive. How can we lower the barrier of entry so that we do not require a developer with NLP background, or in most cases, NLP PhD, to be able to perform all those tasks? So I will talk about how do we address all these requirements in SystemT. Before I do that, let me give you a short history of information extraction. Information extraction is actually a very well studied problem for a long time, and the two general approach. The rule-based approach has started in 1970s from the MAR conference, and the state of the art is considered GATE is considered a state of the art for rule-based system. And then in late 1990s, machine learning became more and more popular. So most of the recent publication on information extraction is on rule-based system.
No. Is Gate the name of a company or company name is different?
You mean Gate?
Yeah.
Gate is actually just the name of the product. It's an open source project.
Oh, I see.
Yeah, it comes from a university.
It's confusing because you said commercial. So.
Yes, a lot of people build a commercial system built on top of it. So last year we actually did a study about how the view of the industry and academia different when it comes to information extraction. And in summary, as you can see here, most publication in academia about information extraction is dominated by machine learning approach. The reason when we look at it because they think it's developed very fast, easy to adopt, and more importantly, you can come up with some interesting formula that you can write in your paper. Then in the commercial world, dominant approach is rule-based system because it's easy to comprehend, easy to understand, it's easy to explain to our customer what happens behind the scene, and it also doesn't require any label data, which is very difficult to get by. So I will talk about SystemT, which is a rule-based system. Before I do that, let me give you a short history of SystemT as well. So we started in 2004, where we want to build a better search system. So we don't really want to build our own information extraction engine at that time. So we tried to write our own customer code, like most people when they started to work on information extraction. Then we found out we need to write so many extractors that is not really very scalable, that you have to write one single piece of new code every time you need a new extractor. Then we look at what's the state of the art at that time. So it is the cascading, the CTSL style cascading grammar. So we utilize that grammar system. Then we identify all kinds of problems that I'm going to describe shortly. Then like everybody else, we did some extension, but still we could not solve the fundamental problem for performance and expressivity. Then in middle of 2006, 2007, we started to think about what if we want to build SystemT from scratch? How should we build it? So that's how today's SystemT come into born. So we approach SystemT. I will talk about the SystemT in more detail, but in general, you can think of SystemT is created with people with database background. Therefore, we approach it with a database bias. I will talk about that shortly. Before that, let me describe to you what's the challenges we have encountered when using the grammar-based system. So the grammar-based system uses the general notion of input text is a sequence of tokens, and then you can express your rules as a regular expression pattern over some lexicon feature of those tokens. So I will show you some examples shortly. And typically, when you use the grammar-based system, you need to do it in multiple levels. That's why it's called cascading. So you can think of at the lower level, I'm piecing smaller things together. As I go higher and higher, I'm piecing bigger pieces together. And the standard for the final state grammar is called the Common Pattern Specification Language. It's a specification of a common language to specify and represent a final state transducer. Every transducer accepts a sequence of annotation and outputs another sequence of annotation. So let's say I have a very simple document that talks about tomorrow we are going to meet someone, and I have very simple first level. I have a very simple rule. I have one dictionary that identifies first name, another dictionary identifies last name, and then I have a regular expression that identifies capitalized words. as we, in the CPSL grammar implementation, you keep a cursor. So you always go from left to right and check which rule would fire. So we go through the first one, like Mark, it will identify as first name. We go to start. Now for start, we will identify it as both first name and the current is slightly different from my machine, but you can think of, for start, it matches both first and the caps. Therefore, I will pick first over caps because the rule priority. So let's say I have the rules of the dictionary have the same priority, which is higher than the rule for capitalized words. So I move again. For Howard, I mark all of them. So now I can decide I want to keep it at first because in the grammar world, when there is a tie, it's first use the rule priority. If the rule priority is the same, it will utilize which rule specified first. So in this case, the first name is specified first, therefore we will mark Howard as the first name. Then we move on to Smith, we will identify Smith as last name. So now we identify all the first name and last name capitalized words for the first level. Then we move on to the second level, where we compose all these first name, last name, capitalized words together into person.
So
let's say,
even in that first level, you don't look ahead to see whether the current word that you're staring at should be classified one way or another way.
correct. In the first level, I do not know about what will happen in the next level. First level, just look at.
No, I'm thinking of maybe something is a place name as well as a person name, but by staring at one more token, you may be able to make a better decision than just saying this rule is before that rule and hence I'm going to classify it based on.
Correct. So you can potentially specify such a rule, but I will show you it's actually fairly difficult to do that. The second level, basically, I compose all these first level tokens that I identify together. So if I say first name and last name, it's a person. If I say first name followed by capitalized words, it's a person. If I say first name alone, it's a person. So now I go through the same process again. So I will know Mark and Scott because they are identified as first name. I will identify each of them as the person. And then for Howard Smith, it matches the first rule, therefore it's a person too. As you can see here, because in the first level, we need to make the decision what Scott is. And because of the rigid rules priority, we will identify Scott as the first name. We now make a mistake when we go to the level 2 because we do not keep track of information. That in level 1, there's some ambiguity when we decide the type for Scott. Another example, we want to identify person phone pairs. So we want to say, this is a simplistic example where we want to say, whenever I say person followed by phone number within the same sentence, I will determine they are related to each other. So here, for example, I have a sentence where this rule happened to match, and the desired result is I want to identify both phone numbers. Now, because in the grammar-based world, we cannot have overlapping output, so it's not possible for me to have the first person phone and the second person phone because they are overlapping with each other, right? Because the second person phone pair is longer than the first person phone pair. Another issue is I could not specify within the same sentence because in the grammar world, I cannot specify predicates that is based on span. It's simply not supported. So basically the second, I can specify something that says person, 0 to 10 token followed by a phone number. I cannot specify within the same sentence. To give you a slightly more complex example, so we want want to identify email signature. It's a very complex problem, although it sounds very simple, but think about all the different ways we can come up with signature. So let's say we come up with a simplified version for identify email signature where we want to find a piece of text that starts with person and then end within 250 characters contains at least two of the organization email or phone or URL and end with one of them. For this, unfortunately, because it requires both counting, because we need to count how many phone or organization URL or those clues within that 250 characters, we cannot possibly express it in native CPSL grammar. So this is another case that we cannot express. So in general, the grammar-based system suffers from expressivity problem because it requires very rigid margin priority, and it also has loss in sequencing because every time the input is a sequence of annotation, output is a sequence of annotation. You cannot have the same token be associated with multiple annotations. And the rule pattern itself has lots of limitations. There are many things that we cannot express. And finally, it also suffers from performance problems. As you already see from our simple example, every time you process one level of the rule, you need to go from left to right over the same document. That means you are scanning the same document many times, although in most cases, you are only looking at a very small portion of the document.
Question. Do you take advantage of an assumption that in a document, the format for putting, for example, names, if they're using first, last, you assume that's carried out throughout the whole document? Or do you always, you don't look at the, you don't make assumptions once you learn, you always go sentence to sentence and they're all independent?
So a document in our world basically is one file.
And do you typically have the same format like for names in a file?
Not necessarily. It can be very noisy. For example, I show the financial reports, right? It's a PDF file with 160 pages. And inside, there are many, many tables. Every table looks very, very different from each other.
And different formats.
Yeah, yeah. In our ideal world, we would like everything to be well formatted, so our job is easier, but in reality, it's very noisy. So these problems are not just what we have realized. So there are many, many extensions that have done by different people trying to overcome all these problems. But unfortunately, none of them address the root problem. So first, for scalability, regardless how fast you make the final state machine can run, it still needs to run through the document multiple times. A lot of times, the passes are unnecessary work. And the expressivity of the language is limited. You can add all kinds of the user-defined function, but it still cannot overcome the fundamental problem of the grammar-based work. And then, because of the system make a lot of decisions behind the scene, it's very difficult to understand why you are getting certain results while they other. And it's very difficult when you make some changes why it's not taking effect as you expected. So we're trying to address all these issues in SystemT. So as I talked about before, most of the people in our group come with database background. So we kind of approach the problem with our own bias. So we identify the most basic operations that require information extraction, and then we create an operator for each of the basic operations. Then we have we allow the user to compose those operators together to construct more complex extractors. The benefit is the rules is much richer and cleaner, and because we abstract the semantics of the rule away from the execution, we will be able to achieve better performance through optimization. So I will first talk about what AQL rules looks like, and then I will talk about the optimization. So you can think of we overcome the scalability limitation by introducing optimizer and avoid wasted work. And we make the rule language more expressive and allow the user to do it more accurately and more transparently. And because we allow user to specify what to extract instead of how to extract, it allows us to build all kinds of tools to help it easier to develop AQL extractors. So this is a simplified version for our data model. So for every document, we assume it has one attribute, which is the original text. And then for each of the objects that we extracted from the document, it has span object with a begin and end offset, as well as a pointer to the original document. So with this, we will be able to recover exactly where it occurs in the original document. And then we have, for every operator in the algebra, it operates on one or more tuple of annotation and produce the list of tuples. In our execution model, we basically do it one document at a time. We process one document, extract everything from it based on the extractor's specification, and then we forget about it, continue processing the next document. So this is different from a lot of approach taken by database researcher, where normally they take a collection at a time execution model. So here is a simple AQL example. We have seen this person phone example before. In order to express this semantics, I basically need to specify three views. The first view is a person view. You can think of it as a table of the person that we extracted from the original document. Then we have the phone number and sentence. What's the first predicate follows told means is basically says identify from all the list of person, all the list of phone number, identify a pair of person and phone where the distance between these two is within 0 to 10 tokens. And the second two predicates basically means there exists a sentence where the same sentence contains both the person name as well as the phone number. So as you can see, we can easily express this pattern in AQL. And here is an example for basic AQL operation. So this is a regular expression operation where we take in input tuple. In this case, it's a document. We run the regular expression over it and obtain all the output tuples. And every output tuple, basically, in this case, is a span object that links back to the original text. In SystemT, we provide a rich set of operators. Most of them are span extracting operators that doing basic extraction like regular expression, dictionary, pattern speech tagging, and then we have relational operator that allow us to combine those things together or do projection and so on. Then we have aggregation operator that allow us to aggregate list of span together. For example, we can group together annotation to produce a longer one using block, or we can do explicit consolidation when words overlapping. And then we have special operators like split and detagging, where we deal with special needs.
So does the span one include the streaming window-like operations where the window can move with overlaps or without overlaps?
Yes, I will show you in an example shortly. So let's revisit our person example. So we basically want to identify, remember in the cascading grammar word we have two levels of rules, where here in the first level, it's actually similar, although it's not really doing in that level. But basically, we first using dictionary identify first name, last name, using regular expression, identify capitalized words. So that gives us a list of tables. So Mohan, come back to your question, you can see the same piece of text in the original document can be extracted into each different list of tuples. So we do not consider the fact some of them may be overlapping. So they are operated independently. And then we can do join, where we say join first name with capitalized word when they are immediately followed with each other. And then similarly, we can say join first name and last name. So that gives another list of candidates. Then we union of them together. Now we will see the overlapping and redundant matches. So remember in the grammar word, some decisions were made arbitrarily by the system. In our world, we do not make any decisions for you. Instead, you will tell us, in this case, for example, you say, I want the longest match. Then we will find the Mark Scott and the Howard Smith as we expected. So this way, we keep all the candidates until the point where you want to explicitly deal with overlapping matches. And this allows us to be able to do it in a transparent and at the same time more accurate way. Now, going back to the person phone example, we already seen how we address it in AGRA. So in the older grammar world, we cannot, even for this simple rule, we cannot express it because of the limited expressivity problem. And in AQL, it's very simple. So we have dictionary identified person, and we have regular expression identifying the phone number, and then we join them together using one single AQL statement, as we have seen earlier. So this way I can get the desired results without any complexity involved. And when we come to the signature, it's also pretty simple. Basically, we identify all these clues that indicate signature individually, and then we union them together, and then we identify a block of text that contains all those patterns, and then we join those patterns with the person, and that gives us the signature. So as you can see, something that we could not even express in grammar world, we can easily express it using AQL. So now revisiting how we address the issue. So for the grammar word, it suffers from rigid multi-routine problem. But in SystemT, we do not have any fixed sequencing, and we return all matches and consolidate explicitly at the user's command. And we do not have the lossy sequence problem because we return all the matches and discard the ambiguous matches explicitly. And finally, we have rich set of operators that including aggregation and counting. In fact, we have formally proved that the class of extraction tasks that are expressible as equal query is a strict superset of that are expressible using the expanded code-free CPSL grammars. So basically that means anything that you can express in grammar, we can express it. But the many things that we were able to express using EQL that cannot be expressed in CPSL grammar without additional customer code. What does this bring to us? The first thing is we will be able to perform tasks much more accurately. So we look at the two example tasks. With SystemT NER extractor built out of box, compare with ANI, which is the NER library in Gates that are built out of box. As you can see, for all the tasks, SystemT perform much better than ANI. Even when we consider partial matches, we are still much better. So as you can see, because we have more expressive language, we will be able to perform much better. Then another question is, can we perform as good as state of the art? We actually asked the question ourselves, and in our experiment, we have answered the question, and the answer is yes. So compared with the state of the art, which are all machine learning based system, as you can see, we have, when we consider F measure, for all the forecasts over different data sets, we perform better than state of the art. And overall, we typically have better precision. Sometimes recall may be slightly lower, but it's not far off. And the advantage of SystemT is especially obvious when we come to noise data like in NRAM, which are email, because there are certain semantics difficult to learn using machine learning model, but it's easier for for a human being to observe and to be able to capture that in a real language. So we have built a long list of libraries based on SystemT. So I have talked about the basic abstraction, like the regular expression, dictionary, color-speed tagging, and so on. On top of that, we can build named entity library, machine data primitives that allow you to do machine log analysis, and also financial primitives allow you to understand the financial reports and life science extraction and so on. So for most of the applications, they do not need to go into the very lower level. Instead, they can build on top of the higher level abstraction that we have already built. So here are some examples of the library that we have.
So I was just wondering, so if you have to do something to deal with noise in the document, would you guys do that, and which level would you do it? Would you do it after you build your table, or would you do it actually after?
What do you mean do what?
Just remove noise or do some sort of disambiguation in the document that maybe there's some typos or stuff that are misleading you, or leading to some publication of those.
Okay. So for people on the phone, the question is about when do we deal with the noise in the document. So it can come in two ways, depending on the type of document. For example, for social media, which is known to be very, very noisy, what we have is we have a text normalization that will normalize the text before we even doing the processing. In some other cases, the noise can come very infrequently. So in other case, maybe instead of build a normalizer, which is very heavy duty, you can deal with it at runtime. For instance, let's say in your document there's some type of person name. Instead of trying to say, oh, I'm going to build a normalizer that deal with all types, I can simply have some dictionary that consider some of the variants of the person name. And that allow me to capture those person name with typo, but at the same time deal with other text as it is. Did that answer your question? Yes or no?
Yes.
Okay, thank you. So these are the long list of extractor library that we have. Many of them are actually not built by us. Many of them are built by software group, by other research teams.
You also mentioned something about the partial match. Do you have an example of that?
Oh, you mean partial match?
Yeah.
Yes. So let's say I have a person extractor, and most of our person extract, let's say I have person extract for English. So for English names, normally at most 3 parts, right? First name, middle name, last name. But now, if I have people from other country where the name can be 4 parts or 5 parts, I may only identify part of that person name. That will cause partial matches. And it could also be our definition of person name can be different. To give you an example, maybe in your application, you want to consider the title of a person as part of that person name. But for the out-of-box person extractor, we do not consider title. Therefore, when I match against your labeled data, I will see partial matches. We also have monolingual support. I will not go into too much details. So performance, we already talked about the performance issue with grammar system because you need to go through the tokens for many times, and most of the classes are wasted work. The dominant approach is to make every single pass faster, but that doesn't really solve the root problem. So in our world, taking the algebraic approach, our solution is build a query optimizer. So what's new for optimizing for information extraction? In information extraction, most of the operations are over text. So they're over sequences and span. We need to consider document boundary and compare to database where the cost is concentrated on join. In information extraction, most of the costs are actually concentrated on extraction. And most of the cost is the CPU cost as opposed to I/O cost. So how do we leverage those characteristics to do text-specific optimization? Let me show you a couple of examples. So this is one example, one kind of optimization we do. So when you build an extractor, often you have many different dictionaries that you specify to extract the lower level features. So instead of run through trying to match each and every single of the dictionary one at a time, we can potentially merge all of them together and match all dictionary in one pass. So this will greatly reduce the cost of dictionary matches. To give you another example, when I have join, for example, I want to join first name and capitalized word together. I know, let's say, my cost estimation tell me dictionary match is much cheaper than regular expression. In such a case, I can first run dictionary, identify all the first names, and only run the regular expression within the vicinity of the first name that I identified. So basically, instead of trying to match through the entire document, I only need to look at a small piece of document that next to the first name. So that greatly reduces the cost of the regular expression. However, we need to be very careful here because when we reduce the rating for matches, we need to make sure we get the same results while we're doing this particular optimization. Similar to a database optimizer, for the same EQL rule, we have different execution plans. For example, I want to join first name with capitalized words. Here are three simple execution plans that I can potentially run. The first one is I do first name, identify all the capitalized words, and then I join them together based on the predicate. Or I can say I identify first name first and then only extract the capitalized word to the right. Or I can say I identify all the capitalized words first and then only look for first name near capitalized word. So these are all possible execution plans that will be considered by our optimizer. Then the optimizer will decide what's the cost associated with each one of the plans and decide the most efficient one. So this leads to significant speed up for our extraction. So here for the same named entity extractor compared to ANI, the open source, the rule-based system, as you can see, regardless of the document size, SystemT is consistently 10 to 50 times faster. And when we consider larger documents, the performance advantage of SystemT is even more obvious. So as you can see, regardless of the document size, SystemT performs much better. And we also consume much lower memory. One thing to note here is, when we talk about memory, it's average memory. In reality, for any, we need to set a very big memory for it to not to crash for some of the documents. So because of the optimizer, we can perform much faster than any with much smaller memory requirement. And we have formally proved that when we, in our optimizer, we will always consider the operator graph that is no more complex than using the finite state transducer. So in other words, we will always consider if there are more efficient plan possible using the finite state transducer, it will be considered by our optimizer. So what it means? Think about when we do Twitter sentiment analysis over Twitter, we need many, many machines using a state-of-the-art industrial system. And when we use the rule-based system, we may require less machine, fewer machines, but when we use SystemT, we can do it essentially with significantly less machines and potentially over on our laptop. So this really reduces the cost, operation cost to do information extraction or to run any application that requires information extraction. So that's what optimization brings to us. And because of SystemT is highly embeddable, we can run it on a laptop or put it as part of Hadoop as the map job, and to be able to scale up. Compared to customized code, where, for example, this is a Java code I need to write to detect sentence boundary, I can do it much simpler using AQL within a few statements. However, in order to write a state-of-the-art extractor, sometimes it can still be very hard. For example, for person extractor, it contains over 250 AQL rules. So how can we help developers to develop this kind of rules of this level of complexity more easily? Or if there's an error, how can we help them identify? So we have come up with all kinds of research trying to deal with problems. This is the life cycle for AQL development. We have tools that help users to identify different tasks, help the user do development, help user to do testing, analyze the results and doing development. We also have tools to help users refine any existing structure and be able to continue maintain it more easily. So a lot of research is related to making it easier for more people to be able to develop extractors.
Quick question. So you talked earlier about this Enron database, and you said there you can measure your accuracy, which means somebody has gone through and found the ground truth. You're supposed to extract people. Somebody went, extracted all the people, and you can see whether you.
Correct.
So you sell this to a customer on their mail database, on their social media, whatever. There is no ground truth.
Mm-hmm.
So where does that feedback come through where somebody who doesn't have a PhD can say, you know, I took that SystemT out of the box, it's not performing well enough. I need to tweak these knobs and get it up to a level. How do you even measure that level of performance without just going in and individually, you know, looking, do I recognize this word right? Do I recognize this sarcasm? How do you do it in an efficient way and not just a picking out spots way?
Yeah, that's a very good question. So the question about when we deployed our existing solution on our client side without labeling data, how can we enable someone to first be able to evaluate the performance and secondly be able to adapt the deployment to their needs? So what we have is we do have labeling tool that allow anyone without any NLP background to be able to highlight a piece of text and say, for this piece of text, it should be person. And then we will be able to take those labeled data and run existing solutions, be able to report precision and recall over the labeled data. And then when there is a mistake, we have provenance tool that can explain where the mistake comes from. And we'll even have tools suggest what are the potential changes that you can do to address all these mistakes.
Right. That will work great when you're making lots of mistakes because you can label almost anything and the tool will get it wrong and so then you'll be able to fix that. When SystemT is not making very many mistakes, then the chances of labeling something at random and having the SystemT screw up is now difficult, right? So how do you continue the optimization up to the point where randomly picking things to label is no longer going to be a good bet anymore?
So that's an interesting point. So the point is, if the SystemT only makes mistakes from time to time, very infrequently, how do we be able to identify those mistakes and fix the deployment, right? So currently we do not have so basically currently the way you deal with it is that you are going to randomly label some of the data. And from that you can estimate, okay, the general quantity is slightly lower than over my development data. And then the user will observe what are the mistakes being making. And if the mistakes, so basically it depends on deployment. So let's say the user doesn't know really how to fix the issue. But what the user can describe is, this is not correct. And then they can explain why it's not correct. So depending on that, we can tell whether it's a definition changes or it's a data problem. If it's a definition change, then that means some additional enhancement is required to deal with that particular new requirement. If it's data problem, what we have is, for many of our existing rules, we have customization points. Like for example, for person, we have a few dictionaries allow you to add to. And using that, you will be able to address most of the false positive or false negative. And in most cases, you will be able to do the customization using those 5 or 6 dictionaries. In the worst case, maybe you will need to develop your own rule and then say, when my rule fires, I do not want any results overlapping with the original results. So that's how you can address the problem. Okay, does that answer your question?
So a common thing like we've been talking about with names and phone numbers, will that rule be general enough that I could just apply it to my data without tweaking it, or do I really have to customize it for each engagement?
So all of the information structure, they are developed over certain development data. So it really depends on how different your data is from that data, and then how different is your requirement from the current implementation. I'll give you an example of, if you require a person containing title, and when I develop my person structure, I do not identify title as part of person name, then you need to extend it. So typically what happens is, you will run the extractor out of box and see what type of mistakes it's making. If it's because our definition is different, or it's because of data characteristics is very different. And based on that, you can customize it accordingly.
Okay, part B. Can I give you an example of my, let's go with this name and phone number. I can give you an example and label it, and could you generate those rules, or do I have to always write the rules? So learn by example.
Yeah, that's a very good question. So if I have, so that's basically active learning, right? So I basically already have set a rule, and then you give me additional example. How do I take that example into account? How matrix the rule? So in our publication or in our research prototype, we do have those things. Like for example, we have work on suggested rule changes. So when you give me some additional label data, I can suggest to you what are the potential knobs that you can tweak. But it's still a research prototype. We do not have it in the product yet.
Could you please repeat the questions so people online can...
Okay, sure. I try to do that. Okay. So the Eclipse tooling, basically we're trying to help it easier to program in AQL rules. We have a lot of different tools like editor, result viewer, labeler, and so on. And then we have tools to help automatic discovery. Like we can generate a regular expression based on like some examples. We will be able to identify patterns giving a list of data, and then we have profiler that can help you identify if there are any bottleneck in your extractor. The latest work that we're working on is web-based tooling that basically requires no knowledge of AQL. You will be able to utilize any existing extractors very easily by drag and drop onto the canvas. And then you will be able to just click on the run button and run it. Then you can compose all these things together, creating new rules. For example, here I'm creating 2 rules, and then I union them together to identify some pattern. So basically, instead of having to learn AQL using this tool, you can build your own extractor within a few minutes without having to learn anything explicitly. So we have a beta out. So if you are interested in trying it out, let me know. In summary, SystemT is a declarative information extraction system. We have cost-based optimization, high-performance runtime, novel development tuning, and we also have solid theoretical foundation. It's currently shipped with 10+ IBM products and installed on over 400 client sites. So we have talked about development environment. So AQL, we have a lot of paper describing what AQL is and show how it can outperform in the state of the art. And a lot of our research, as I have talked about before, is on novel development tuning that leverage in machine learning and HCI. And our cost-based optimization also generates a number of publications. And we have described our runtime, how it's embeddable and with very high throughput and small memory footprint. And all this has been embedded in different IBM engines and can be embedded in any pipeline using Java API or different wrappers. So for big insights and streams, these are fully exposed AQL and engine with the tuning. And we have different products using SystemT behind the scenes for their extracting tasks. So in the future, what we would like to do is we want to do additional runtime improvement and expand its core functionality. For example, we are embedding deep parsing capability into SystemT. And we also want to continue working on the optimization. One direction is to use hardware to accelerate the extraction process. And then we want to continue enhance AQL. Believe it or not, even after 7 years, we're still getting requests for additional features to put into AQL. For instance, recently we added some way for people to embed the table function that allow you to embed a machine learning model to run inside AQL. And we are building more and more generic library, so we do all the hard work and other people can just use it and can do it with very simple customization for their work. And more importantly, we are building more powerful tuning to allow more and more people be able to utilize information extraction. So before only developers understand how to build a extractor, now we want to enable our business user to be able to do that as well. So if you want to know more information, I have lots of pointers here. So visit our website, our internal wiki, And if you want to learn AQL, some of you already attended our 3-day tutorial this summer. You can learn it, so we share all the materials online. You can learn it at your own pace. If you really want to get dirty and learn stuff about AQL, you can just take one of the lecture and one of the lab, so you can learn AQL in under 4 hours. We also have SystemT weekly half hour at the Art Lab every Tuesday, 1:30 to 3. We have a group of people here. And if you have any questions, feel free to contact me or any of the SystemT team members. Thank you. Any questions?
Can you integrate this with systems of record to do some of the checking that you talked about earlier? For example, if you had Blue Pages available to you, and you knew this was emailed from IBM, then you could verify that the names are people who are in Blue Pages.
I will answer the question. So the question is, if we have some internal data like Blue Page that can help us verify whether a certain entity exists, how can we utilize that in information extraction? This is actually a common scenario where we somehow need to combine internal data along with external data during the extraction process. What you can do is, in the case of a Blue Page, for instance, or a person name from Blue Page, you can create a dictionary or a mapping table. And then you can use that as a basic predicate. So for example, you have person extractor, and you can say, give me all the person that matches this dictionary from Blue Page. Then that allows you to identify all the persons that are IBM employees. Similarly, if you, for instance, in the case of sentiment analysis, a lot of time you care about what people talk about my product, right? So therefore, you will have a product catalog that you will check against to say, giving all the sentiment mentions, identify which one actually mentions my product. So you will.
I don't know.
Okay. So any other questions?
So I have a question. So if I have to use SystemT for writing a concept extractor for the medical healthcare, then I have to probably build my own dictionary and to start with that first, and then write my own operator or functions.
You write your own AQL rules.
AQL rules.
Yeah.
And I expose this as one single function, just like you have person or something. I mean, how do I make it simple enough to be used by other people?
You mean?
So once I have the extractor, once I have done all the hard work of building the dictionary and have written the code, so the code would be the AQL, or would it be exposed as a function that someone can do?
Okay. So basically the question is, once I have built an extractor, how do I use it in my larger application, right? So it can come in two ways. One is you can use a raw AQL, and then at the runtime, you can call SystemT, compile that AQL, and then run it, get the results, using Java API to read the results, and feed into the high-level pipeline. Another way is when you create, let's say, within the Eclipse tuning, you can compile it. You can compile it into a time file that can then be executed at the runtime using SystemT. And similarly, you read the results of the extractor and then feed into high-level pipeline.
So I had a question. Early on you had a chart where the academics are all doing 80% of their work with machine learning. And in industry it's much more rule-based, but it wasn't 0% machine learning. So my question is, what is it about this information extraction task that a machine learning system seems to be really good at, and rule-based systems like SystemT seem to have difficulty?
Okay. So the question is, when I talk about earlier in this slide, there is one slide about most of the academia people focus on machine learning, but in industry we focus on rule-based system. But is there a way to basically leverage this tool? Is there any way that we can leverage the machine learning in the rule-based system? This is actually much of our research focus on. How do we leverage machine learning for rule-based system? So in our development tooling, a lot of the work is on how do we use machine learning to learn basic features like learn regular expression, learn dictionary, and also how do we learn to make rule changes, or in some cases, how do we learn rules from scratch? Because the benefit of rule is that the rule is transparent, it's understandable, and it's very easy for us to incorporate any domain knowledge as required. But come up the rule, writing the rule can be very time consuming, especially, for example, for dictionary. Instead of you have to manually collecting every single entry, what about I provide some seed and then you give me candidate and I can add it to my dictionary. Similarly, how about I provide some examples of the chemical compound, you come up with a regular expression that can capture all of those. So a lot of machine learning are happening behind the scenes in our world. And that basically allows us to get the best of these two.
You mentioned that you have about 250 AQL rule for main extraction. So 250 about the right the number. All I need is if I 40 plus client, do they just use this with sufficient, or do they need to add a lot of more to find the right name? Second part of the question is, this is for Western English language. How about like Chinese?
Okay.
For Chinese, the main extraction will that be you have the library for it, or how do you define?
Okay. So there are two questions here. The first question is on this slide, I'm showing the building size and stream with SystemT engine installed on 400 plus client size. How many of them actually using the out-of-box solution, and how many of them actually build their own rules? The second question is, what's the support for languages such as Chinese or Japanese? For the first question, I don't know the exact number about how many of them are actually writing their own rules, but for the 400 clients, for most of the POC I was involved, our client actually the person who was writing AQL rules. For example, when we were giving the summer tutorial here, we actually got a request from our client that they want to attend the tutorial themselves as well. So most of them, once they realize the value of the AQL, because within there, a lot of the companies, they are doing information extraction themselves. So once you realize AQL can help you do the same thing much faster, more efficiently, and more accurately, they actually are fairly willing to switch to using AQL. So for the second question of support for languages such as Chinese, we actually have good coverage for Chinese. So for Chinese, we have out-of-box solution for named entity and for sentiment extraction also for both traditional and simplified Chinese. Any other questions? Okay, thanks.
Thank you very much.